Hello, and welcome to another episode in the Lytron Line Learn series. I'm Dr. Jeff Bemis, and I'll be your host for this session. The in vitro micronuclease assay is a type of chromosome damage assay that is routinely performed as part of product safety assessment studies. If you are unfamiliar with this flow cytometry-based assay, I will begin with what a micronuclease is, and then go on to discuss more about our particular methodology. If you watched the Learn 101 episode on in vivo micronuclease, this cartoon will look familiar. But there are a few important differences to note here as part of in vitro micronuclease biology. In the middle of the diagram, you will see mitotic cells, in this case cultured cells, that are experiencing one of two types of genotoxic damage. The cell on the left side was exposed to a clastogen, and you can see that a small acentric fragment has broken off of the chromosome by virtue of a DNA double-strand break. Upon division, this fragment does not get reincorporated into the nucleus of the affected daughter cell, and thus remains free in the cytoplasm of the cell. The cell on the right side of the cartoon was exposed to an angiogenic agent that disrupted the spindle fibers responsible for tethering the chromosome to the corresponding centrosome. This disruption means that the entire chromosome is lost to the cytoplasm and, like the acentric fragment, is not reincorporated into the daughter cell nuclei. Since we are performing this study in cultured cells, there is no nucleation event to take advantage of like there is in the erythrocyte micronuclease assay. Thus, we have to take a different approach to enumerating cells with micronuclei. I will cover that in the next section. So that's a brief look into micronuclease biology in the context of cell culture. I will now go on to describe the sequential lysis and staining protocol that is used to process these samples, and then highlight some specific characteristics of the in vitro micronuclease assay that differentiate it from other methodologies. This schematic shows the multiple processing steps involved in the in vitro microflow method. At the top, we see cells that have already gone through a typical exposure period, for example, 24 continuous hours. We can see that there are several different states that the cells may be in depending upon the exposure conditions, those being normal, healthy cells, cells with a micronucleus in the cytoplasm, cells going through cell death processes, such as apoptosis, and cells that are clearly necrotic or dead. The first step is to incubate the cells with nucleic acid dye A, which will enter into cells with compromised plasma membranes and bind to DNA. Here we're using a red color to show the uptake of the dye in the necrotic and apoptotic cell populations. A visible light source is then used to covalently bind this dye to the DNA, and this is important because of the next step in the procedure. If you watched the Learn 101 class on in vivo micronuclease, you will remember that enumeration of cells with micronuclei was made simple based on the fact that erythrocytes do not have a main nucleus, and thus no additional nuclear material to interfere with visualizing micronuclei. Cultured cells do not undergo this process. Thus, in order to separate the nucleus from any potential micronuclei in the cell, we use a detergent to lyse the cells, thus liberating both nuclei and micronuclei. This lysis is accomplished simultaneously with the addition of nucleic acid dye B, which labels all nuclear material in the lysed sample. In this case, we use the green color to show the single color staining of the nuclei from healthy cells, and the nuclei and micronuclei from cells that have undergone genotoxic damage. The nuclear material from the dead and dying cells are stained both green and red, thus allowing us to readily identify and remove this population from subsequent analysis. This is the basis for the in vitro microflow assay and allows us to examine nuclei and micronuclei separately. The next slide shows the two flow cytometry plots in our gating scheme that enable us to identify and eliminate or enumerate the desired populations. Let's focus on the left-hand side first, where we have the nucleic acid dye A, or ethidium monoazide bromide, on the x-axis, and nucleic acid dye B, or cytox green, along the y-axis. The events in the lower right are positive for EMA, which you will recall could only enter the cells with compromised membranes. Since we lock down the dye by covalently binding it to the DNA, it remains in place even after the cell lysis procedure. Using the flow cytometer software, we then exclude any events in this region of the plot, thus reducing the influence that these interfering particles may have on the enumeration of micronuclei. The nuclei and micronuclei are then examined on the plot to the right, which separates the population based on size or forward scatter along the y-axis and cytox green fluorescence along the x-axis. Since the nuclei are larger and contain more DNA, these events end up in the upper right portion of the plot, while the smaller, less nuclear dense micronuclei fall in the lower left portion. The gating we apply here captures micronuclei that are approximately between 1/10 and 1/100th the size of the main nuclei. Following exposure to a genotoxic agent, we see an increased accumulation of micronuclei events in this region with increasing concentration of test article. One other important aspect of the in vitro micronucleus assay that is directly addressed by our method is the evaluation of cytotoxicity. The potential genotoxic effects we wish to discover are, by definition, cytotoxic, but there can also be secondary effects of overt cytotoxicity that can be interpreted as genotoxicity. In order to mitigate against this unwanted influence, methods for in vitro micronucleus should include assessments of cytotoxicity, and current guidelines recommend that cytotoxicity levels of no more than 55 plus or minus 5% should be evaluated for micronucleus formation. To obtain the values required for calculation of cytotoxicity, our in vitro microflow method incorporates a counting bead that is distributed equally across all samples. When you use this particle to generate a nuclei to bead ratio, you can compare across samples to determine the impact of exposure on the cell culture density. In this cartoon, we see several mock sample tubes, starting with a control sample and moving through increasing concentrations of a cytotoxic test article. As one would predict, the number of nuclei decrease with increasing loss of cells by toxicity, but the number of beads remains the same. In this example, we would also exclude the samples furthest to the right, as it exceeds the percent cytotoxicity limits set forth for this assay. Collectively, the overall evaluation of genotoxicity in each sample includes not only the induction of micronuclei and the indicator of cytotoxicity I just described, but we also have other indicators that can be used to flag certain conditions that may contribute to the final outcome. Information on cell cycle, such as a G2M delay one often sees with clastogens, can be obtained from our method, along with certain indicators of genotoxic mode of action, such as an increase in hypodiploidy. All of this information is obtained simultaneously in each sample analysis. In the interest of time, I will discuss this and other mode of action assessments in more detail in subsequent videos. Okay, I hope you're still with me. I'm now going to go into some specific aspects of the in vitro microflow assay and how they relate to assay conduct, study design, and other important considerations. These topics are compatible cell types, assay format, sample format, and regulatory considerations. Finally, I will end by addressing some of the upcoming Learn classes that will go deeper into this particular methodology. Historically, L5178Y and CHO cells were probably the most commonly used cell type for in vitro micronucleus. But more recently, human TK6 cells have become the de facto standard due to their p53 status and the fact that they are derived from the more relevant human model. In vitro microflow is compatible with all these suspension and attachment cell types, as well as numerous others. If you are interested in a particular cell line and you can't find its use mentioned in the literature, please contact us and we will help you determine the feasibility of your proposed studies. There are multiple assay formats to choose from, depending on your study design and desire for rapid throughput of large libraries or comprehensive assessment of a few compounds. The means to perform all of these approaches are provided in detailed instruction manuals and even analytical templates for certain flow cytometry software packages. Litron is also very focused on customer support, so if you run into any trouble using our assays, you can speak directly to the scientists that develop these methods, and we will get you back on track to conducting your important studies. The entire assay, including exposure, processing, and analysis, can be accomplished in 96 or even 3D4 well plates if you have a flow cytometer equipped with an automated high-throughput sampling device. This can enable walk-away analysis and evaluation of many compounds in a short period of time. Of course, standard higher volume formats, such as T-flasks or large well plates, can be used if you have the need to split off cells for multiple assays and endpoints. In terms of regulatory considerations, the OECD 487 test guideline is the guidance that specifically addresses in vitro micronucleus methodologies. If you are a study director, technician, or even a sponsor, and you are tasked with performing a micronucleus assay, I highly recommend that you refer to this test guideline for expert consensus on the conduct of this method. In this section, I also want to point out the ever-increasing role that in vitro methods, such as cell-based micronucleus assessment, are having in hazard ID and risk assessment. Concepts such as quantitative dose-response analysis and point of departure metrics, such as benchmark dose, fit nicely with in vitro microflow's high-throughput formats that allow you to examine many concentrations in multiple replicates and thus develop the most accurate picture of exposure-related genotoxicity. Extending this further to in vitro to in vivo extrapolation takes advantage of the comparable nature of micronucleus biology across our methods and the numerous benefits of flow-based approaches. The ultimate role of in vitro microflow and other such assays in this context is still under investigation, so please dig into the literature or have discussions with knowledgeable people if this aspect of the method interests you. So what's next for our method? I plan to create some Learn 201 level classes that will go into further detail on the topic of genotoxic mode of action studies. These will likely include information on our in vitro multi-flow systems as well, so if this interests you, please keep your eyes out for these videos in the near future. Beyond that, I also have plans for a Learn 301 level class that will address cytotoxicity assessment for the in vitro micronucleus assay in much greater detail. Again, stay tuned for that as well. And with that, I would like to conclude this Learn 101 introduction to in vitro microflow. I hope you come away from this with a better understanding of how micronuclei in cultured cells represents a useful indicator of chromosome damage in vitro, and how our flow cytometric methods easily accomplish this important methodology. Our method's ability to provide comprehensive information on genotoxicity as well as cytotoxicity, in addition to rapidly scoring large libraries of compounds, are just a few of the benefits that make this the best way to achieve this important endpoint. Please contact us to set up a discussion about your needs or to learn how to access any of our kits and services. Thanks again for your attention, and I'll see you next time.